So today I'm going to talk to you about ionization energy. So we previously defined ionization energy as the energy required to remove the most loosely bound electron in an element or in an atom that's in its ground state, and that's generally when it's a gas. So what I'm going to talk to you today about are the trends in ionization energy, so you understand what's going on with that. So we can look at the trends in ionization energy going down a group. So when we look at ionization energy going down a group, what we'll see is that the ionization energy, that the ionization energy will decrease. And when we look at ionization energy across a period, we'll see that the ionization energy will increase. So we have these two different trends. So let's talk about ionization energy going down a group, why that happens. Well, when we go back and look at the radius, we saw that the radius going down the group got bigger. So that means that that outer electron is further away from where the nucleus is. So when we think about it being lost, if that electron is further away from where the nucleus is, then it is going to be less attracted to the nucleus. That lower attraction is going to cause the electron to be more easily removed. So let's write this down. So as the radius gets larger, the valence electron is further from the nucleus. As that radius gets larger, the valence electron is further from the nucleus. And that means that that valence electron is less attracted to the nucleus. And that means that it takes less energy to lose. So that would be lower ionization energy. So this is going down a group, and you can see if you look at the ionization energies down a group, they generally decrease pretty systematically. But when we go across, we see that the ionization energy goes up. So why would the ionization energy go up? Well, we can go back to radius again. When we look at the radius is getting smaller. So now the electron is closer to the nucleus. It's more attracted to the nucleus. So we almost have the opposite here. Radius goes down. The valence electrons are closer to the nucleus. So that means that they are more attracted. And if they're more attracted, it will require more ionization energy, more energy to remove that electron. Now, if you were taking Regents chemistry, the story would stop there. We would say that these are the general trends. But unfortunately, going across a period, it's not just so straightforward. There's some exceptions going on here. So if we look at this, if we go across, if we start at lithium down here, and I highlight this, lithium going over to sodium, the general trend is to go up. So I'm not lying to you and telling you ionization energy is going up, and it's not. But the problem is that there are some blips. Like, for example, if we highlight here, there's a decrease from beryllium to boron, and there's a decrease from nitrogen to oxygen. And those are exceptions. So let's look at these two and why they are exceptions. So let's look at beryllium versus boron. Well, beryllium has 4 protons. Boron has 5 protons. So it has more protons. That means that this has a higher nuclear charge, higher Z, and this has a lower Z. Yet, when we look at the ionization energy for these, the ionization energy for beryllium is about 900, and for boron is about 800. So there's a little bit of a dip. Now, why does this happen? Well, let's look at the electron configuration. For beryllium, it's 1s2, 2s2. For boron, it's 1s2, 2s2, 2p1. Now, maybe you're thinking to yourself, oh, it has to do with the electron configuration, and if you're thinking that, you're right, it does. Well, what's going on here is that these 2s electrons over here, these are shielded by the 1s, whereas the 2p electrons over here are shielded completely by the 1s, and then shielded a little bit by the 2s. So all by the 1s and a little bit by the 2s. And so if I had to put this into words, these 2p electrons are more shielded in boron than the 2s are in beryllium. So, boron has a slightly lower ionization energy. There's a little bit more shielding going on there. That means that the electron, even though it is closer overall, it's also more shielded. And that then leads to a lower ionization energy. The other exception was nitrogen and oxygen. So nitrogen and oxygen, again, this has 7 protons, this has 8 protons. So this has a higher Zeph, or higher nuclear charge. When I look at the ionization energies, again, what I see is that this is around 1400 and this is around 1300. Those are the ionization energies. So what's going on here? Why is this happening? Like, why do we have a decrease there? Well, let's look at the electron configurations. Maybe we'll see that shielding effect again. So for nitrogen, we have 1s2, 2s2, 2p3. And for oxygen, we have 1s2, 2s2, 2p4. So we can't really say that it's the shielding at this point. We can't say that. What could it be then? Well, maybe we have to draw out the electron configurations. So when we look at 2p over here, we see that we have 1, 2, 3 for nitrogen. When we look at the 2p here for oxygen, we have 1, 2, 3, and 4. What do you think's going on there? Well, if you're thinking about it and you're saying, well, this electron over here, it's paired up. That's what's going on. So over here, this is a case, and one of the rare cases where you have more electron repulsions. When you have those more electron repulsions, then you get this situation where the ionization energy is decreased, because that extra repulsion, it will actually overcome the increase in protons. So look, when I go back and I look at the overall trend here, I can see that the trend is going up. From lithium to neon, there's an increase in ionization energy. But there's these 2 exceptions that seem to crop up across every period. They get less and less of an effect as you go down in the periods. So from period 2 is where we see the biggest effect here. You see it in period 3, but then it sort of goes away over here. You have phosphorus to sulfur versus nitrogen to oxygen. You don't see that same decrease. We can talk about why in class. That's a little bit of an extension of this. But we have these 2 exceptions that you're required to know. We have the beryllium-boron exception, and that one has to do with the fact that the 2p are better shielded than the 2s. And then you have the nitrogen-oxygen, and that's due to the extra repulsion in the oxygen atom. Now, there's something called successive ionization energies, which they don't touch in regions, but I'm going to talk to you about for a minute or so. And so, the question comes up on the SAT. So, we only talk about on the regions this first column here, the ionization energy number 1 for the first electron. But you can remove more than 1 electron from an atom. It may not happen naturally under certain circumstances, but we can get it to happen in a laboratory. So let's see what happens. When we have sodium here, removing the first electron took about 496 kilojoules. When we remove the second, it jumps to a whopping 4,562. Well, let's see what's happening with sodium. So with sodium, we have an electron configuration of 281, if I draw it out the simple way. When it becomes an ion, so this is Na, when it becomes Na+, it becomes 28. Now, if it's going to become Na plus 2 and remove that second electron, it would become 2-7, Na plus 2. Now, the difference here is this first electron over here, this was removing a valence electron. When I look at this one, now we're removing a core electron. And so what we see is that when you start to remove core electrons, there's a huge jump. Those electrons in the core are much closer to the nucleus, they're much more attracted to it. If I pick an element like, aluminum here, so I have Al as my 283. So it could become Al plus and become 282. It could become Al plus 2 and become 281. It could become Al plus 3 and become 28. And then it could become Al plus 4. And that would be 2-7. So now, when we remove the first 3 electrons from aluminum, we are removing valence electrons. So let's look at aluminum here. To remove the first one took a little bit of energy. To remove the second electron took more energy, because now we have a positive ion, the electrons are more attracted. When we have removing the third, we have more energy. But now we're done with the valence electrons. We remove the 3 valence electrons. Let's go into the fourth, into the core. And when we try and remove that, look at this huge jump. It jumps up to 11,000. So there's this huge difference, this huge jump between valence and core electrons. And so we see that with the successive ionization energies. And the question that you see, they'll give you like element X, and they'll give you, all the successive ionization energies, and there will be this huge jump. And you have to look at it and say, the huge jump was here, so that means that it had this many valence electrons. Okay, well, I'm going to stop here for ionization energy. Next time we'll do electronegativity and different properties. We'll finish off the notes with the last video. All right, thanks so much for watching.